The paper proposes a novel trustworthy utility evaluation framework with counterfactual explanation for simulated SAR images, denoted as X-fake. It unifies a probabilistic evaluator and a causal explainer to achieve a trustworthy utility assessment. The evaluator is constructed using a probabilistic Bayesian deep model to learn the posterior distribution, conditioned on real data. Quantitatively, the predicted uncertainty of simulated data can reflect the distribution discrepancy. The causal explainer is built with an introspective variational auto-encoder, intro-VA, to generate high-resolution counterfactuals. The latent code of intro-VA is finally optimized with evaluation indicators and prior information to generate the counterfactual explanation, thus revealing the inauthentic details of simulated data explicitly. The proposed framework is validated on 4 simulated SAR image datasets obtained from electromagnetic models and generative artificial intelligence approaches. The results demonstrate the proposed X-fake framework outperforms other IQA methods in terms of utility. Furthermore, the results illustrate that the generated counterfactual explanations are trustworthy, and can further improve the data utility in applications. Evaluating the quality of simulated synthetic aperture radar (SAR) images is crucial for various applications. Traditional metrics like mean square error (MSE), peak signal-to-noise ratio (PSNR), structural similarity (SSIM), and visual information fidelity (VIF) assess image quality based on human visual perception. However, these methods may not be trustworthy for SAR images due to their specific imaging mechanism. The Frechet inception distance (FID) is also widely used, but it relies on pre-trained ImageNet inception networks, which may not be suitable for SAR images. The utility of simulated SAR images is worth studying, particularly in real-world applications where deep neural networks are trained with both simulated and real data. Some works focus on utility evaluation in terms of model performance, such as the substitution rate curve (RSC) criteria and the hybrid recognition rate curve (HRR). Others aim to improve the data utility of simulated SAR images using transfer learning, domain adaptation, or knowledge distillation. Uncertainty quantification and explanation are essential for trustworthy AI. Methods like Bayesian neural networks, ensemble methods, and test time augmentation can estimate uncertainty in deep neural network predictions. However, explaining the source of uncertainty is equally important. Researchers have developed methods for explaining complex supervised learning models, but explaining uncertainty has received relatively little attention. The proposed X-fake framework addresses the utility evaluation problem by quantifying the domain shift uncertainty of simulated SAR images. It consists of 3 steps: constructing a probabilistic evaluator (PIVA) with a Bayes CNN model, pre-training an intro-VA model for high-quality counterfactual generation, and optimizing the latent code to obtain the counterfactual explanation. The probabilistic evaluator is constructed using a Bayes CNN model, which features 4 trainable layers and 2 branches for target category prediction and azimuth vector regression prediction. The Bayes CNN network can capture the uncertainty of predictions by incorporating a probability distribution for its weights. The construction and optimization of the Bayes CNN can be realized using different methods, including Bayes by backprop and Monte Carlo dropout approximation. The algorithm involves assessing the utility of simulated data by quantifying the uncertainty of the recognition model outputs. The optimization problem is transformed into the latent space of the pre-trained intro-VA model, making it easier to optimize the counterfactual explanation. The proposed framework provides a unified, trustworthy, and explainable method for evaluating and improving the utility of simulated SAR images. The posterior distribution of Bayes CNN parameters is learned using variational inference, which approximates the intractable true posterior distribution. The evidence lower bound, ELBO, is maximized to regularize the weights. The Kullback-Leibler difference between the simple variational distribution and the true posterior distribution is minimized to learn the Gaussian distribution parameters. The objective of the research is to develop a Bayesian convolutional neural network (Bayes CNN) for synthetic aperture radar (SAR) image evaluation and counterfactual explanation generation. The Bayes CNN is constructed using 2 methods: Monte Carlo dropout and local reparameterization trick. The Monte Carlo dropout method approximates a probabilistic deep Gaussian process, while the local reparameterization trick optimizes the variational posterior distribution. The Bayes CNN is trained to predict the category and azimuth angle of SAR images, along with their corresponding uncertainties. The uncertainty is calculated using the category uncertainty and azimuth angle uncertainty. The category uncertainty is given by the difference between the frequentist inference and the Bayesian average of predictions, while the azimuth angle uncertainty is calculated as the variance of multiple samplings. To generate counterfactual explanations, the research proposes to utilize intro-V, a probabilistic generative model, as the foundational structure of the explainer. Intro-V consists of an encoder and decoder that can project high-dimensional data into low-dimensional latent space. The encoder is trained to minimize the KL divergence between the posterior and prior distributions, while the generator is trained to minimize the reconstruction error. The counterfactual explanation generation involves optimizing the latent code Z to minimize the distance constraint, prior category and angle information, and predicted uncertainty. The optimization is performed in the latent space using the pre-trained encoder of intro-V. The counterfactual explanation in the image domain is generated from the pre-trained decoder of intro-V. The research also proposes to use the difference between the counterfactual explanation and the original image to report the inauthentic details of the simulated SAR image. The difference is multiplied with its absolute value while keeping the sign, and the positive and negative values are colored with red and blue, respectively. The experiments are conducted using a real SAR image dataset and 4 simulated SAR image datasets. The results are presented in Figure 4, which shows some examples of the experimented datasets. The paper discusses the evaluation of synthetic aperture radar (SAR) images generated by advanced generative AI approaches, including SARACGAN, SARC, and SARN-ERF. These datasets are compared with real SAR images from the M-STAR dataset and M-model-based simulation data from the sample dataset. The goal is to assess the distribution inconsistency between real and simulated data using a novel evaluation method that does not require paired data. The proposed evaluation method utilizes a Bayes CNN model trained on real M-STAR data at a depression angle of 15 degrees. The model is then used to evaluate SARACGAN, SARC, and SARN-ERF data with a depression angle of 17 degrees. The input size of the evaluation model is 88 × 88, and the training data are pre-processed with center crop, logarithm, and random grayscale stretching for data augmentation. The results show that the proposed evaluation method outperforms other full reference and non-reference IQA methods in terms of utility. It achieves the highest performance gap, indicating its effectiveness in evaluating the utility of simulated SAR images. The paper also explores the effectiveness of different Bayes CNN models, including EVA-BBB and EVA-MCD, and demonstrates that EVA-BBB can achieve better performance in evaluation. Additionally, the paper presents 4 paired examples of real and simulated images, showing that it is difficult to distinguish the quality of these images from a visual perspective. However, the proposed method can successfully assess the simulated SAR images in terms of data utility, even when they have similar visual quality. Finally, the paper discusses the recognition versus substitution rate curves, RSC, as a dataset utility evaluation index. The RSC results of 3 simulated SAR image datasets are presented, illustrating the global utility of the datasets. The proposed explanation method evaluates data utility for each sample with a quantitative metric, allowing for the filtering of high-quality data. The method is demonstrated to explicitly reveal the inauthentic details of simulated data through visualizations of original simulated images, generated counterfactual samples, and explanations of inauthentic details. The counterfactual explanation is shown to improve the data quality and utility both explicitly and implicitly. The effectiveness of the proposed explanation method is verified through quantitative experiments, where the ACON-VNet model is trained on different simulated data and tested on real M-STAR target images. The results show that training with full original simulated data causes a dramatic decrease in classification accuracy, while the generated counterfactual explanation can improve the data utility. The proposed method is also shown to be effective in improving the utility of different deep learning architectures, such as ResNet 18, ResNet 50, DenseNet 121, and SWIN transformer. The utility evaluation results and counterfactual explanation results of 3 AI-generated SAR image datasets are presented. The results show that SAR-CAE data are generated by the fewest training samples and can perform comparable utility with SAR-ACGAN, where the training data are doubled. The counterfactual explanations of SAR-ERF and SAR-CAE data are more effective than those of SAR-ACGAN data, improving the image utility better. Ablation studies are conducted to verify the effectiveness of each module in the counterfactual generation process. The results show that the recognition model trained directly on original simulated data and tested on real data obtains a baseline result. The counterfactual explanation method, using VAE as the generator and optimizing with distance and uncertainty, shows a slight improvement over the baseline. The addition of class guidance and intro V further improves the utility of the generated counterfactual data. The recognition versus substitution rate curves, RSC, are applied to evaluate the simulated SAR image datasets in terms of utility. The results show that the proposed explanation method can improve the data utility, making the trained model more applicable. The experimental results demonstrate the effectiveness of the proposed explanation method in improving the utility of simulated data. In this paper, a novel trustworthy framework, XFake, is proposed to evaluate the simulated SAR images and explain the inauthentic details of them from the perspective of data utility. The proposed framework comprises a Bayesian convolutional neural network-based probabilistic evaluator to output predicted uncertainty and a generative model-based causal explainer to obtain the counterfactual explanation. The predicted uncertainty of simulated data reveals an inconsistent distribution with real ones, which can be regarded as a criteria for utility assessment. The counterfactual explanations are generated with prior information, including the target label, azimuth angle, and the predicted uncertainty from the evaluator. It demonstrates the inauthentic details of the simulated image that cause the inconsistent data distribution. Experiments are conducted on several simulated SAR image datasets generated by both EMBASED and Gen AI-based approaches. The results illustrate that the proposed evaluator can successfully filter out high-quality data in terms of utility, while the trained deep learning model can achieve higher performance on real SAR images. Additionally, the generated counterfactual images explicitly improve the utility of simulated data. The classification model trained on generated counterfactual images outperforms the ones trained on original simulated data by 30%. The hyperparameter discussion reveals that with the increase in the proportion of angle loss, the azimuth angle of the generated counterfactual image is more accurate, and the recognition model trained with these counterfactual samples performs better on azimuth angle regression prediction. When lambda y, lambda v equals 130, the result achieves the highest classification accuracy on the test set. The influence of lambda d is also experienced, where a larger lambda d would result in less change from the original image, leading to inferior counterfactual results. The proposed framework provides a new approach for evaluating the utility of simulated SAR images and generating counterfactual explanations to improve the utility of simulated data. This approach can potentially enhance the performance of deep learning models in SAR target recognition tasks. Here is the combined summary of pages 13 and 14. The authors present a comprehensive review of image quality assessment, uncertainty quantification, and Bayesian deep learning methods. They cite numerous studies on image quality assessment, including those using no reference metrics such as BRISQUE, NIQE, and PIQE, as well as those using reference-based metrics like PSNR and SSIM. The authors also discuss the importance of uncertainty quantification in deep learning models, highlighting the need to estimate uncertainty in image quality assessment tasks. They cite studies on uncertainty quantification methods, including Bayesian neural networks, dropout, and ensemble methods. Furthermore, the authors review various Bayesian deep learning approaches, including Bayesian convolutional neural networks, Bayesian neural networks with variational inference, and introspective variational auto-encoders. They also discuss the importance of uncertainty quantification in SAR image generation and target recognition tasks. The authors also cite studies on image denoising and despeckling, highlighting the importance of preprocessing filters and discrete wavelet transform-based noise reduction techniques. They also review studies on SAR image denoising using variance stabilization and non-local filters. Lastly, the authors highlight the importance of probabilistic perspectives on generalization in deep learning, citing studies on Bayesian deep learning and uncertainty quantification. They emphasize the need for further research in this area to improve the reliability and robustness of deep learning models in image quality assessment and SAR image analysis tasks.